This is Professor Dare of Science, solving equations. Equations are balanced. They have a left-hand side and a right-hand side that must always remain equal. Equations can contain one or more variables, numbers, and operations. Solving an equation is the process of finding the values of its variables that make it true. Solving an equation is a progressive, step-by-step simplification. There may be a series of groups of steps that reach progress milestones. These steps here are simplifications. These level platforms are progress milestones. At the top is the final solution to an equation. Simplification occurs via inverse operations, also known as reverse or undo operations. Here is a table of inverse operations frequently used in solving equations. They are the operation and its inverse. They are both inverses of each other. In this table, we're applying them in one direction. Add and subtract. You subtract a from a, you get 0. Multiply and divide. If you divide a by a, you get 1. Power and root. We look here at an nth power of a, and then take an nth root of that, and you get a. That's if n is even and a is greater than or equal to 0. We'll see other cases for n in the examples. Distribute and factor. Here is a distribution, AB plus AC. The common factor of a can be just factored out to get a times the binomial, in parentheses, b plus c. Exponential variable, logarithmic variable. This equation has a base of b and a power, an exponent of x. The variable's in an exponent. If we apply the log base b operation or function to that, these are inverses, and they effectively reverse each other, and you get x. Breaking apart and combining. Here are two fractions with the same denominator, c. You can combine them because they have the common denominator to be a plus b over c. Swap sides. If a is equal to b, then you can write b is equal to a. Add, subtract example. Starting equation, x plus 3 equals 9. Our first step, subtract 3 from both sides. The reason is to eliminate that 3 on the left for a simplification. 3 minus 3 is 0, and 9 minus 3 is 6. We're at the final step of this solution. X is 6. 2x equals 10. Divide both sides by 2. 2x over 2 is 10 over 2. The 2 times x and the division by 2, they reverse, cancel each other, and you just get the x is equal to 5. Power and root examples. First with odd powers, taking 3 here. X cubed equals 27. Take the cube root of both sides. Cube root of x cubed is x. Cube root of 27 is 3, because 3 times 3 times 3 is 27. Cube root, not cube root, x cubed equals -8. Solve that one. Take the cube root of both sides. Cube root of x cubed is x, and cube root of -8 is valid because it's a -2. -2 cubed is -2 times -2, which is positive 4 times negative 2 is negative 8. That's valid to take a cube or an odd root of a negative. On the right, even powers and even roots, x squared equals 100. Take the square root of both sides, and x is the square root of 100. However, plus or minus will both work, because if you square 10, you get 100, and if you square a negative 10, that's negative 10 times negative 10, you get a positive 100. X squared equals negative 100. Trying to take the square root of both sides will not stay within the real number system. A square root of a negative gets into the complex number system, and so there's no real number solution, which is the context that we're dealing with now. Distribute and factor example. The original equation, 8x squared plus 3x equals 0. There's a common x in each term. We factor it out, and we now have x times the binomial, in parentheses, 8x plus 3 equals to 0. This is a product, a multiplication of two expressions. Use the zero factor property. A product is 0 if and only if one or both of its factors are equal to 0. Set x equal to 0, one factor, and x plus 3 equal to 0, the other factor, and solve each of those simpler equations. X equals 0 is already solved. 8x plus 3, subtract 3 from both sides and divide by 8. You get negative 3 over 8, and that can be written as negative 3 over 8 because a minus sign in a fraction can be moved from the top to the bottom or to the front without changing the fundamental value of that fractions ratio. Exponential and logarithmic variable example. The original equation is an exponential equation. The variable is in an exponent. The base is e, which is not a variable. It's a irrational number like pi. Take the natural log, which is a base e logarithm of both sides. The notation for that is ln. Normally it's log with the base. This would be log little e, but the shorthand notation is ln. So take ln, the natural log of both sides. Here, the base e and the natural log are inverses, so what comes out of this is the 2x plus 1. They cancel out, and you get the 2x plus 1 equals natural log of 5. Subtract 1 from both sides and divide by 2 to isolate the x, and you have here an exact answer, natural log 5. And then minus 1 divided by 2. Using a calculator, you can calculate what this expression is equal to and round it, in this case, to 4 digits of precision. Break apart and combine example. X plus 2x over 3 equals 20. Take the first variable here, the first term, x, and expand it to be in a non-reduced form. Change it to be 3x over 3, which is equivalent to x. And now there's a common denominator between these two fractions, and they can be combined, added. 3x plus 2x over 3 is 20. Multiply both sides by 3 to get rid of the 3 down here. And, well, we didn't do that yet. One step that is shown next, following the flow here, is we add the 3x and the 2x next. They're like terms, and you have 5x over 3 equals 20. And now multiply both sides by 3 to clear out the 3. 5x equals 60. Divide both sides by 5, x equals 12. Swap sides example. The original equation here. First, clear out the parentheses by distributing this 3 across this binomial. 3 times x is 3x. 3 times negative 2 is negative 6. So the original 18x plus 3 times parentheses x minus 2 equals 20x is now 18x plus 3x minus 6 equals 20x. Combine the 18x and the 3x on the left-hand side, that's 21x. Subtract 21x from both sides. On the right, 20x minus 21x is minus x, and we're left on the left with a minus 6. Minus equal to a minus. You can multiply both sides of this equation by -1 or divide both sides by -1 to get rid of those minus signs. 6 is equal to x, and to make this in the natural left to right way that we read things, swap sides, x equals 6. You can swap sides at any step. Here it's done at the very end. Solving equations containing fractions. The same equation we just solved doing a combination. There's a more effective way, a general way, multiplying both sides by the least common denominator, the LCD, of all fractions involved will eliminate all the fractions from an equation. There's only one denominator here, 3, so the LCD is 3. Multiply both sides of this equation by 3. You have to use parentheses on the left-hand side because it's not a single term, it's a binomial. Distributing the 3 on the left, 3 times x is 3x. 3 times the second terms, the 3's cancel, leaving just the 2x. On the right, 3 times 20 is 60. Combining on the left the 3x and the 2x, you have 5x equals 60. Divide by 5, both sides, x is equal to 12, which is the same answer we got up here when we did this by the combine method. Formulas. Solving an equation for a variable. An equation with n variables, where we're dealing here with n more than 1, like 2, 3, 4 variables, can be rearranged into n different formulas. A formula is where one of the variables is isolated by itself on the left-hand side. Here's an example. Solve this equation, z equals x minus mu all over sigma. Solve it for x. This equation happens to be the formula to calculate the z-score for a value in a distribution with a mean of mu and a standard deviation of sigma. But oftentimes you will want to go the other direction to be able to calculate x given the other values. Multiply both sides of this equation by sigma to clear out the sigma denominator, and then swap sides. You'll have sigma z now on the right and x minus mu on the left. Add mu to both sides to get rid of the minus mu, and x is equal to sigma z plus mu, now a formula in x. And if you know the values of the other variables, you can substitute them in, plug them in, and get your answer. The quadratic formula can be used to solve any quadratic equation when it's written in standard form. A quadratic equation is a second-degree equation, has an exponent of 2 on the variable. This is standard form here, ax squared plus bx plus c equals 0. It's possible to use algebra to solve this general standard form, but you don't want to do that every time. So once you know the answer, you can use the formula called the quadratic formula immediately and save you a lot of time. Here's the formula. X will be negative b plus or minus. That means plus this and minus this. Two different possible solutions here. Square root b squared minus 4 times a times c, this whole thing over 2 times a. Depending on the value of the b squared minus 4ac, which is underneath the square root, we'll label that with a variable capital D, which stands for discriminant. Depending on that value, you can either have two distinct real number solutions. If D is greater than 0 because of the plus and minus, you'll get one, what's called a double real number solution, but it's only one solution. If D is equal to 0, because the square root of 0 is 0, and plus 0 and minus 0 is still 0, and it doesn't change the answer. Or if D is less than 0, you're taking the square root of a negative, which puts you in the world of complex numbers. And those solutions will be two conjugate complex numbers. As was mentioned, D is called the discriminant. Solving a system by substitution. Substitution is a general equation solving technique. A system of equations is two or more, in this case, two equations. That's what those braces mean around them, that it's a system. One is x plus y equals 1. The other is x minus y equals 1. The goal is to find values, ordered pairs of an x and a y, that when you substitute them into the original equations, both equations will be true. The whole system will be solved. We'll first solve this using substitution. First step, take the first equation and rewrite it as a formula for y. You do that by subtracting x from both sides. Y is 1 minus x. Next, take the second equation and replace the y by 1 minus x, what we just solved for. So we'll be substituting into the second equation x minus, you need the parentheses here because you're subtracting a binomial, 1 minus x will be equal to 1. Solving this equation, distributing the minus sign, that's minus 1, and a minus is a plus x. X plus x is 2x. Adding 1 to both sides, we get 2. Dividing both sides by 2, x is 1. So we know the first coordinate of our solution will be 1. Taking that 1 and substituting it into this y equals 1 minus x formula in place of the x, so we have y equals 1 minus 1, and we get 0 for the answer there. So the ordered pair 1, 0 solves this system. Let's check. 1 for x, 0 for y. 1 plus 0, well, that's 1, and it is equal to 1. 1 minus 0, that's still 1, that's equal to 1. That ordered pair solves this system. Here's the same system, and this time solving it using elimination. In elimination, we immediately apply inverse operations to eliminate one of the variables. Adding these two equations, since they're both equations, if you add them, you'll get an equation that's valid as a result. You have to have the variables lined up in order to add them conveniently. So x plus x is 2x. Y plus a negative y, those are opposites. That's the same as y minus y. That's 0. Cancels out. They're inverses. 1 plus 1 is 2. 2x is 2. Divide both sides by 2. X is 1. So we've quickly got the 1. Now, take the first equation and plug the 1 in for x. 1 plus y equals 1. Subtract 1 from both sides. Y is 0. A very efficient, more elegant solution to this system. Rounding intermediate calculations. Some solutions require multiple calculator calculations and an approximate, rounded final answer. To maintain accuracy, avoid excessive intermediate roundings because every rounding is a loss of part of the value of the number. May be small, but they can accumulate if you do several of them before you get to your end result. For example, if your final answer needs 2 decimal places of accuracy, you could round intermediate results to 4 decimal places if you have to do any rounding. Frequently using a calculator technology, you can do your calculations and wait till the end to do the rounding. But if you want to present intermediate results in some kind of a visible format, you can have roundings along the way. As shown here, don't round like you want your final answer, but round to a more precise precision, because you know you're going to lose a little bit every time you round, and you'll be okay at the end. Here's an example of rounding particular numbers to 4 decimal places. The ... indicates that they have some higher precision going off here that we're not interested in. 4 decimal places go to the 4th position after the decimal point. It's underscored here, 0, 3, and 1 in these 3 example numbers. And then look to the right. If the number immediately to the right in the 5th position is less than 5, you don't change the number before it. So the 0 remains a 0 here because we have a 0. The 3 remains a 3 because we have a 4. If the number to the right is 5 or greater, then you're going to round up. So this 1 becomes a 2. Standard rounding conventions. Experience. The best way to improve your equation solving skills is to gain experience solving a wide variety of equations. This can only occur as you learn new techniques and develop more mathematical maturity. An important part of this process is to learn from your mistakes. If you make a mistake, understand how it happened and don't go down that error-prone path again. Try to avoid repeating mistakes. Another key aspect is to solve equations in the context of real-world problems and applications. We'll look at a couple of those simple context kind of problems where equations come up. And here we'll also see that there are alternate solutions to problems. There is often, if not always, more than one way to solve a problem. For this diagram on the right, we're asked to determine the length of the arc labeled with the variable s here. Before we look at the alternate solutions, let's take in what we're given, understand the geometry, the landscape of this problem. There's a circle centered at the origin. Inscribed inside the circle is a square. And looking at the coordinates of the points, the vertices of the square, we can see that this square has a side length of 2. There's 1 here, 1 there, adds to 2. There's a smaller little square in the upper right quadrant of the bigger square, and an angle there that is the diagonal of that little square, so it bisects the angles where the vertices are. And since this is a square, we have 90-degree angles, and bisecting one gives you 45. We have a 45-degree angle, labels as theta. This little triangle is a right triangle. R stands for the radius of the circle, and 1 and 1 are the sides of this little square. S is an arc on the circumference of the circle, and we want to calculate S. How long? What is the measure of that arc? Our first solution, we'll use the arc length formula, which is a formula in trigonometry. It's S equals R theta. S is the arc length, R is the radius of the circle, theta is the central angle that cuts out that arc on the circle. First, we'll use the Pythagorean theorem to find R. If you remember the little right triangle there, Pythagorean theorem, the hypotenuse squared is equal to the sum of the squares of the legs. So R squared is 1 squared plus 1 squared equals 2. Taking square root, r is square root of 2. Next, since this arc length formula requires theta to be in the unit system called radians, not degrees, that's the natural measure of angles, we use a conversion formula to convert theta to radians. That formula is that 1 degree is equal to pi over 180 radians. Multiplying both sides by 45, remember our angle was 45, 45 degrees then is 45 times pi over 180, and 45 goes into 180 4 times. We end up with pi over 4 radians is the radian measure for theta. Going back to our arc length formula now and substituting for r, we substitute the square root of 2, and for theta we substitute pi over 4, and multiplying what we did here is rearrange, so this becomes the square root of 2 over 4 times pi. That's an exact answer. If we want a decimal approximation, use a calculator. This is rounded to 4 decimal places. An alternative solution to the same problem is to use circle symmetry. First, we'll use the circle circumference formula. The circumference, which is all the way around a circle, is pi times its diameter. Next, again, use the Pythagorean theorem, just like we did in the previous slide, to calculate r. R is the square root of 2. Find the diameter of the circle. That's simple. The diameter is twice the radius, so that's 2 times the square root of 2. Going back now to our circumference formula, plugging in pi times diameter. Well, pi is there. The diameter is 2 square root of 2, so we get 2 square root of 2 pi. And now use circle symmetry. This arc, looking at this diagram, this picture, is half of the first quarter of the circle. So it's 1/8 of the entire circle, 1/8 the circumference. So S, which is what we're looking for, is 1/8 of the circumference. That's 1/8, 2 square root of 2 times pi. Here the 2 and the 8 cancel out to get a 4, and you end up square root of 2 over 4 times pi, just like we arrived at in our previous solution, and the same decimal approximation.